Hello and welcome back to question 4 part 1. This is a curve sketching question. This question says that the curve C has the equation y equals to f of x, where f of x is a rational function given by the question to be this. Now what a rational function means is just that you have a function in your numerator and a function in your denominator. Okay? And a has to be a positive constant, meaning that it is non-zero. It's important later on. So part 1 says to find algebraically, meaning that you cannot use a GC, you cannot use a sketch to assist you. You have to show in terms of just steps and algebraic manipulation that what are the set of values y can take. Now what do we mean by the set of values y can take? Let's look at conceptually what's happening. Now you can think of f as a machine, where if you put in x, then your output will be f of x, where f of x is the rational function. Now, if we let y is to be the output, then what are the different outputs that we are going to get? Now, what you should be thinking of is x is not a single value. X is a continuum of values, right, from positive infinity to negative infinity. If you take all these inputs and stuff it through the machine, you're going to get a variety of outputs. Now, it turns out in this question, or for this rational function, right, the outputs, they're not across all of the number line, but they could be in, separate regions like that. And that's what the question wants. Can you tell me what are the regions on the number line that the values of y can take? What are the set of values for y? Now, we can, this would be a lot easier if we can draw, a graph or sketch, But since you have to do it algebraically, I guess there are a few ways we can do this. Right? If you read the solution to this question online, they are given a very short and very elegant solution to this. Meanwhile, I'm going to do something different. I'm going to do something a longer way so that maybe you get a bit more clarity. After all, this is a video to help you with revision. I will try to cover as many things as possible. So what I'm going to do instead is, going the long way, I'm going to pretend that I'm going to sketch this graph. Because after all, in part 2, we are going to sketch this graph. I'm going to make use of part 1 to collect all the information that will help me towards sketching this graph. So number 1, to sketch a graph, we need 3 things. We need the asymptotes, the stationary points, and where it cuts the x or y axis. Number 1, I'm going to find the asymptotes. To find the asymptotes, we need to deal with this rational function because it is not in a proper form. To be in a proper form, the numerator must be in a degree that's lower than the denominator. Now, what does that mean? It goes back to Sec 3, AMAT's polynomials, right? So, a quadratic function, as you can see, which is in the numerator, has a degree 2. The denominator is degree 1, is a linear function. So, I need the numerator to be in a degree that's lesser than the denominator, meaning that I can only allow constants to be on the numerator. So, how can we whittle this down to just a constant in the numerator? This is what we can do. So starting with y, starting with this, my next step is to make a simple substitution. I'm going to substitute a with a negative a plus 2a. Now why have I done that? That's because I can write it as 2 separate fractions like this, and then I can cancel off x minus a. Yes, I was trying to force the x minus a to appear so that I can, cancel it out with the denominator. And that's nice because then I get an x plus some other fraction. Now, for that some other fraction, I'm going to repeat the same trick. Right? This is the same as 1. Okay? So then I have an x minus a that cancels out, and this is my final form of f of x. F of x is actually equals to x plus 2a plus 2a squared over x minus a. And this final form has a lot of information in terms of asymptotes. Why? Now let's look at the last rational function over here, right? This tells me that, hey, this fraction over here will never go to 0 as long as a is not 0. And we are assured a is not 0 because a, like I said earlier on, is a positive constant. So if this is not 0, then the smallest value we can take is when x is very, very positive or x is very, very negative, much larger than a. Right? Much more positive than a or much more negative than a. What happens is this becomes a very large denominator with a very small numerator. And what's going to happen is this one will go towards 0, but it will never be actually 0. And that means that my f of x, my output, will never be x plus 2a. It will always be x plus 2a plus some small value. And that is my first asymptote. Right, my first asymptote is this line over here. Right, y equals to x plus 2a, gradient of 1, intercept of 2a. Right, sometimes the graph may cross over, right, but for large parts of the graph, it will never touch this line. That's my first asymptote. For my second asymptote, you can see is x equals to a. How do we get that? Back to our rational function at the end over here. If x is equal to a, then I get a division by 0, and that's an undefined answer. So we're going to exclude that as well. So now that I got the asymptotes, the next thing is to find the stationary points. Right. So for stationary points, we're going to do a differentiation, dy dx. Right. Remember that y is equal to this. If I differentiate this, I'm going to get this. Right. And I'm going to let dy dx equals to 0. Right. Which means that, I can do some manipulation. I'll get this. I'll get a quadratic in x. I can use the quadratic formula to solve for x, which eventually gives me this. And then I'm going to substitute this into y to get the different y values, right? Because I'm hoping to see a maximum or minimum point. So substituting this into y, the positive value, a plus a root 2, I'm going to get y equals to this value over here. And it's very tempting at this point to say that, hey, x is more than a, because we have an asymptote, right? A over here. A plus something that's positive must be on the right of this asymptote. Okay? And if you look at the y value, it's 3a plus 2 root 2a. So it is more than 2a. It's above this point here. So I can say that, hey, this point is somewhere over here. It must be a minimum point. But you must remember at this point that we are supposed to do this algebraically. We cannot use a sketch to assist us. So that means I'm going to do a second derivative test. That means I'm going to do a d squared y dx squared. Again, if I differentiate dy dx, I'm going to get this. Then I'm going to substitute in both the values. Right? The positive value, a plus a root 2, and the negative value, a minus a root 2. How do we know that a minus a root 2 is negative? Because root 2 is about 1.414. So a minus 1a minus 1.414a is going to be a negative value. So when we substitute this in, first I'm going to substitute the positive one in. Okay, before we talk about this, let's look at d squared y dx squared first. d squared y dx squared has a numerator that's always positive. Right? 4 times a squared, that's always positive. So whether d squared y dx squared is positive or negative depends on the denominator. So I'm only going to look at the denominator here. When I substitute the positive value of x, right, what I'm going to get is this. This cancels with this. Then it will be cube root of just this term here. And that is positive. If d squared y dx squared is positive, that means this is a minimum point. Yeah, this will give me a minimum point. As we have suspected over here, earlier on, we have suspected it to be a minimum point over here. Right, but now I've done this algebraically. Yes, it's a minimum point. I'm also going to substitute the negative value of x when x is equal to a minus a root 2. Again, this cancels out. It will just be the cube root of a negative value, which is negative. So d squared y dx squared is negative, which means this is a maximum point. Okay? So coming back to the graph, I have a minimum point here. I have a maximum point somewhere over here. Okay? So the range of values that y can take, yeah, we can visualize with a number line. It is going to be more than the minimum point and less than the maximum point. Okay. Again, this is not an acceptable answer because we're supposed to do it algebraically. We have to get the set of values. So I have to write it in curly brackets, set notation. Right. Y belongs to the set of real numbers because it's not just integers or fractions. It is all numbers, all real numbers. Right. Such that y is less than this value, 3 minus 2 root 2a, and y is more than 3 plus 2 root 2a. And that is the answer for part 1. Right? This is a much longer method, but I tried to cover more things in terms of revision. Now, I hope to catch you in part 2 and part 3. See you in the next one.